Can't find it. So what is mechatronics?
Mechanical, electronic, mechanical, electronic.
Well, originally, that's what it started out to be. It was actually, I forgot the name of the person that actually coined the phrase, but it was over in Japan, and they realized they were working on systems or technicians needed to have skills in not only electrical or electronic, they also needed to have experience in mechanics. But over time, if we come over here and just look it up, and people still have problems. We even had our PR lady, Gary Albright. She came over here and she was talking to us, and then when she wrote up the article, she put it down as Megatronics. And then we had Sarah Versler came out and did it for whatever channel she's on. And when that's what she called it, when she was doing her thing, her voiceover, she called it Megatronics. Because people understand Megs, they understand that. And even though we're saying mechatronics, that's what they hear because that's what they're familiar with the term Meg, even though nobody has any idea what mechatronics actually is. This didn't turn out too good, guys. So let's see if we can find another image. I don't know what happened to my. It's called mecha for mechanical, right? Tronics for electronics. And it's full. And we'll go to images and see how big these are. Can y'all see that? So this is what it's turned out to be. It's basically mini trades, right? You understand? So mechatronics, control systems, control electronics, electronic systems, mechanical systems, mechanical CAD, control systems like PLCs. So it's a well-versed thing that is incorporated in the term mechatronics now. So y'all understand that? So there's a lot involved. I guess it would be, CAD is computer aided design. I guess it would be designing mechanical systems with the aid of a computer. They don't talk about, we do have electrical or electronic design applications that we have available, but it's not listed. Most of CAD systems are mechanics, right? You understand when you design the actual physical aspects of a device, that's more mechanical than it is electrical. But I've never heard of it called mechanical CAD. And we can look, we could go over here and look at all these different images. And there were some neat ones which I was looking at. No, y'all can't see that. I have to zoom on it. But they probably don't say mechanical CAD, but they've got simulation. Yeah, but they just don't say mechanical CAD, right? They just say CAD. It's trying to. I don't know if it's going to pixelate on us. Mechanics, electromechanics, electronics. I can't see what this says. Transducers, which are So what is a transducer? What is a transducer? I think we talked about that in the last class. What's a transducer? It's something that takes energy in one form and converts it to another form. So there's a lot of devices that are transducers. So even a grist mill or a water wheel takes flowing water and converts it over to mechanical energy. That would be a transducer. So a transducer is a device that takes energy in one form and translates it over to what? Another. Control circuitry, microcontrollers, simulations, digital control systems, computers, computer-aided design controls. So here they don't call it mechanical CAD. Like I said, I haven't heard that term used before. And I've got one that's really neat. It might be in the folder. And I thought I had a PowerPoint made up of just what mechatronics was, but I couldn't find it. I don't see it. It's taking a little while for it to convert these over. So when we talk about mechatronics, we're talking about a wide variety of topics, right? So electrical, over here we're going to talk about electrical, electronic, mechanical, fluid power, and PLCs. That would be the computer portion. Of course, what we're going to do is we're not going to look at the programmable controller from the inside. We're going to look at it from the outside, right? How do we connect to it? And basically what it does, not how. What does programmable mean? It means it is, right, it's changeable. We can change what it does by changing a program, right? You understand? So it means all these PLCs back here, you might see this PLC like the Siemens 314s, which is what we got over here on the Amatrol line. You might see it running this, but you just might as well see it running a drill press. You might see it running an elevator. You might see it running an air conditioning system, right? Because they're totally what? Programmable, which is neat. And this is really, PLCs have really changed the way automated systems work. Because now we can take a little box and make all the decisions of my system and then still be able to control things. So electrical, and this is what we were talking about the other day. I think we went through here. DC, AC, everybody okay there? Some of y'all hadn't had AC yet? Oh, AC. And we talked a little bit about this. Some of y'all that was here, AC and DC are not the same. And I'll try to go show y'all something that's really weird about AC. But of course, DC. What is DC? What'd you say, Brian? So what does that mean? It never changes direction. It can change amplitudes, but it never changes. So I could have 0 right here, and I can have it do like that, and that's still DC because it never changes polarity. If it never changes polarity, then the current never changes direction, right? So you might see it on one of my tests. What's the difference between AC and DC? And one of them says DC never changes amplitude, and you know that's false because if it was, we'd be screwed, right? Every battery I bought would have to be a certain voltage. Every car battery would have to be the same. Well, they are, but it can never change, right? You understand? So that DC can be all over the place. In fact, most of our audio amplifiers are DC amplifiers. And the way they work is they put the audio on top of what? Just make it superimpose it on DC. And then we got devices that can strip that off. The DC will have a 0 reference point, and then that's 0. It could be up this way, and then it would be positive DC, right? Or it could be what? It could be down here, and then it would be negative. But it never goes negative if it's positive, and it never goes positive if it's negative, right? Understand that? Which means the current flow would be in the same direction. AC, we got all forms of AC. The one that we'll primarily deal with is called an AC sine wave. And I'll draw it the best I can, but it changes like this. And this is the way Alabama Power sends power. And at 0 volts would be something like right around here, right down the center. So, of course, what happens is that this thing crosses 0. How much work do we get when it's right here? They don't get any work, right? Because we don't have any current flow. You can't have current flow without a difference of potential. So there's points in the waveform that we have absolutely no current flow. And then it'll take off really, really fast. Then it'll go up here and it'll hit a peak. Here we have maximum current flow. And as soon as we have maximum current flow, it does what? Starts dropping down, hits 0 again, and then what does it do? Changes polarities, so the current would do what? Would change direction. And then down here, so if this is what we call a symmetrical waveform, then this, we call this an alternation, by the way, for all this reason. So we have a positive alternation, we have a negative alternation. The positive and the negative alternations are mirror images of each other. So if we had a way to flip them over and bring them together, you couldn't tell them apart, right? They're perfectly the same. This is the way we generate power. It's generated on what we call a cycle, which would be one repetition. You got your lights on at home. These things are changing constantly. It changes at a precise rate. We call that the frequency. And the frequency, we call one of these repetitions, we call this a cycle. Because that's what a cycle is, right? It's like years are a cycle, days are cycles. Every day, as far as the number of hours we have in a day, is exactly the same, right? The number of minutes we have in a day. And then when we hit 12 at night, what does it do? Starts over. But you got to understand, that's what this guy is right here. You have to understand the ending of this cycle is the what? It's just like 12 midnight. What is 12 midnight? It's the ending of this day and what? The start of the day. So 12 o'clock midnight is two things at the exact same time. So here, this would be one cycle. And then we have the rate of, so a cycle is the repetition of a repetitive rate, one repetition of a repetitive waveform. And then we have the rate that they occur. So frequency is the what? This is the rate of the cycles. And so Alabama Power generates 60 cycles per second. Now, and this is the way we talk about, we said, okay, this has been around. Anybody that's fundamental in developing the rules of physics usually has their name given the honor of being named for something. So we have a guy named Hertz. So usually you hear 60 hertz, and that's what it means, 60 cycles per second. So I mean 60 cycles per second. That means one whole cycle from start to finish would take 16.2 6666666 or 16.7 milliseconds. So how long is it at that peak right there? We just can't understand that, right? You understand? Because we're dealing with 60 milliseconds. For one alternation is only 8.333333 or 8.3 milliseconds. And this is Alabama Power. The higher milliseconds reach, the higher the frequency, the shorter the cycles. Now, what advantage AC has over DC is we can transmit power magnetically. So to produce an EMF magnetically, we have to have a magnetic field. And if you're ever over in the motor controls lab, we've got a big old magnet that came out of an old disk drive, big drives. And it's and we got a coil of wire. And we'll take that coil of wire and we'll swing it across that magnet. And we have a little ammeter up there, and you'll see every time I swing across that magnet, it produces current flow. So what it does is we have a magnetic field. Then we have a conductor. And I'll talk about this in just about every class. And then we have what we call relative motion. What do we mean by relative motion? What do we mean by relative motion? Well, it means one's got to move in relation to the other. So we can hold the conductor stationary and move the field. This is what your alternator does. So your alternator is spinning a magnetic field. And where you're getting your power off, we don't want to get our power off of something spinning because we'll have to use slip rings and stuff, right? Understand? So what we're producing the voltage into, or the power into, is what we call the stator, or the stationary part, or the stationary winding, excuse me. And we got a lot of turns and we're spinning it. And every time it cuts one of those bundles of wire, it does what? It produces a voltage. Now, what determines the amount would be the strength of the field. You have to excuse my writing. My screen bounces when I'm writing on it. The number of conductor loops. So basically, what we do on every little loop wire is we get, every time we move in one direction, we would get a little small battery. And then if we wind the wires in the next direction, then what we're doing is we're hooking up these tiny little old batteries. In fact, I shouldn't be drawing them as two cells in series. So series 80 means what? All these things are going to do what? Add together. So we have all these turns of wire. They just wrap and wrap. Number of turns. And number 3 would be the speed of the motion. So what we do on your car is that the magnetic, I don't have my electromagnet in here, but so anytime we put current through a conductor, it creates a magnetic field, right? And then we can use a chunk of metal to concentrate that field. But what's nice about electromagnet is we can do what? We can control its what? Strength. The more current we put into the thing, the stronger the field is. The less current we put into it, the weaker the field is. So what you have on your car is you have what we call the rotor, for obvious reasons. It's an electromagnet that's made up of a bunch of wires. And then I'll have what we call a set of slip rings on the back of it. These are just copper things, and then you'll have brushes riding on the slip ring. But we're just controlling the strength of the magnetic field, so you're not getting the power off of it. You got a lot of turns of wire, so it's not taking a lot of current to get a really, really strong magnetic field. And now the problem we have with a car is we're constantly changing what? The speed of the motion, right? You understand that? You know, you're sitting out there idling, your alternator's turning fairly slow, right? You understand that? You go fast, but what would happen if we didn't do something? You know, you're sitting there and your car is idling, your lights would be off, your air conditioner wouldn't be working, you couldn't raise your windows up. You get up to 70 miles an hour and it blows your lights out and burns everything up in your car because we're putting too much energy into it, right? But what can we do? Well, what we do is we have a regulator that's monitoring the output of our alternator. And if it drops down, what do? Well, they increase the strength of the magnetic field. They just put more current into the rotor, right? So when your car goes fast, what do? They decrease it, right? And so we have what we call a regulator. So that's what's really nice. So what we can do is that if I put current flow through a wire, it creates a magnetic field. Then I can come up here and put another set of wires that's got a bunch of loops in close proximity to this. And then I can couple them with some bars that move through there. I can transfer energy without actually having a mechanical connect or electrical connection between these two. And we call these guys what? Warmers. So what we can do is we can change the ratio of the number of turns between the side that's pointing toward the power source, and it's called the primary. And then the one that's pointing toward the load, we call that the secondary. We can change the ratio, and we can either step the voltage up or step the voltage down. And that's the advantage of AC. Because what we can do is we can step it up for transmission because it takes less current, right? The big problem people don't understand about power is I'll say, okay, what does a transformer do? And most 90% of the people says it steps the voltage up or steps the voltage down. But what we have to understand is that we cannot create energy. Work in equals work out, right? If the system was 100% efficient, then work in and work out would be equal to each other. We can't get more work out than we do what? Put in. That makes sense. So what a transformer don't do is a transformer don't change the power. So if the transformers that our power company used were 100% efficient, that means you turn on a 100-watt light bulb at your house, Alabama Power would give you 100 watts. Y'all understand that? And it would be 100 watts through the whole system, right? You understand that? Because power in equals power out. Actually, the formula is power in equals power out times the efficiency. So in efficiency is always going to be what? Less than. Because there's nothing that's 100% efficient. Nothing. No matter what people tell you. There was a video on YouTube where a guy hooked up a generator to an electric motor, and he plugged the thing in to get the motor up and running. He plugged it in to get the motor up and running, and then he unplugged it and it kept running. And he said the alternator was putting out enough, the motor was spinning the alternator fast enough to keep the motor running. Is that possible? Yeah, so they had the motor turning an alternator. And then what they did is they got the thing up to speed and they unplugged the motor. And then they used the power of the alternator to supposedly run the motor. Is that possible?
Oh, better.
He had some kind of trick going because that's totally impossible. We had a guy that come up with a great idea. He says, we got these battery, this is a true story. We got these battery powered forklifts at our work. I'm going to take generators and put it on the wheels of the forklift. And as they drive the forklift, I'm going to use that to charge the batteries. And he said, and he thought he had this great idea. And I says, the batteries are going to run down faster. Because now it would take 100 watts of energy to get the alternator running, but you'd only get like 90 watts out, right? Because the alternator would never be 100% efficient. So where would that, well, it would come from your source. So what would happen is they would run them faster. Now cars kind of cheat because we have the ability to have hills and stuff. So what, some of your cars will actually charge the battery when the car's going on downhill. But no, nothing's 100% efficient. So we don't ever happen, but if we consider this to be 100% efficient, then this would be 100 watts in, 100 watts out. But what happens on our transmission, power is equal to what? V times I, right? So I would be equal to what? P over V. So if I'm trying to give you I'm trying to give you that 100 watts, the higher I can make that voltage, well, the less current is going to be required to give you that. That makes sense? Because Alabama Power is not selling you voltage. They're not selling you current. It's not even their name. They don't call them Alabama Voltage. They don't call them Alabama Current. Why are they selling you? Power. Because they're selling you work. Power is work, right? That makes sense? So that's what they do when they're transmitting that stuff, and they got to go through all these different wires and all these transformers and all this kind of stuff. They step that voltage up what? Really, really high, which causes the current to do what? Drop down so they can get it through the resistance of the system. And this is what I say, some of the interstate lines, they get up to about 750,000 volts. With 750,000 volts, they could send 750,000 watts of power with 1 amp of current. Right? You understand? Now, what advantage does low voltage have over high voltage?
Safe.
Yeah, that's right, safe. I didn't get it out yet. So the closer they get to us, they're going to have to start lowering that voltage down, which causes the current to go up. But current's what kills you, right? You understand? I understand that, but I is equal to V over what? Over R. So the lower we can make that voltage, I can say, and I hear this all the time. I say that car battery out there can put out, good gracious, probably 200 or 300 amps, depending on what you got. Will it kill you? A car battery. How many of you touch the leads of the car battery on yourself, right? You understand? Just because a source has that potential, if it don't have enough, I is not equal to the amount of current that's available from the source. I is equal to V over R, right? So it's how much voltage you get into and how much resistance your body has. You could get into a source that's got 1,000 amps of current available, right? You understand? But it's only at 12 volts, would it? It's almost impossible for a 12 volts of push to do what? Pushing the current through your body to do what? To kill you. Yeah. So yeah, your car battery's got 12 volts out there. And it might have a couple hundred amps available, but it's I through your body is equal to what? How much voltage your body gets across, and how much resistance your body has between the two contact points. So this is why we have AC. AC, it automatically creates this. It automatically creates what? Motion. So it's constantly doing what? Magnetic field comes expanding out, cuts through your secondary. As soon as then it collapses back, changes direction, so it automatically creates relative motion. And it automatically induces voltage into conductors. So we have what we call induction motors that only run off AC because the magnetic field in the rotor is induced into it by an AC source. So AC motors are a lot less expensive per horsepower. We can send AC over great distances, but with high voltage, right? You understand? When Edison discovered DC, and learned how to generate DC, he was trying to power up. I don't remember. I think the city was Chicago. I need to go back and look at that. We got a really good video about the history of electrical power grid, and he was like having to put a generator station every mile, because trying to send that amount of current through those conductors, and every conductor has resistance, right? You try to send a lot, and the voltage drop was just unbelievable. So they had to have a steam generator every mile to do what? To regenerate and support the power grid. And then when Tesla invented AC, so DC was discovered, AC was what? Invented. Tesla, yeah. That's why a lot of people don't know about Nikola Tesla. He invented AC. And it's a really, really interesting story. Edison was DC. Tesla was working for Westinghouse, and he was AC. And they had a big. Edison was trying to show how more dangerous AC was to get electrocuted. He's killing elephants and things. He was electrocuting elephants with AC. It's a really good story. And he was trying to convince people not to trust AC. And then they had a big World's Fair out there, and they chose AC over DC, which was really interesting. And Edison invented the light bulb, and he wouldn't let them use their light bulbs. So Westinghouse had to invent their own light bulbs so they could put them. It's a really, really interesting story. But I think it's called The History of Electricity or something like that. It is a really good video.
The car named after him.
Right, because nobody knows. Everybody knows Edison because of all his other inventions. But Tesla was an inventor too. He's one of the guys that was really, really smart. So he was one of those guys that had that technique to just see how things would operate. Ohm's Law, you okay with Ohm's Law? What does Ohm's Law give us? Ohm's Law gives us the relationship between the voltage, the current, and the opposition, not necessarily resistance. We have three oppositions in an AC circuit. In a DC circuit, we got one opposition. That's called resistance, and that's what you learn in DC. If you take AC, which unfortunately it's not in the AUT degree, we pick up two more oppositions called reactance. One is called reactance. Reactance is a weird thing. Reactance varies with frequency, but it's an opposition. It's in ohms. It's in ohms, guys, but it varies with frequency. And we have two devices that are reactive. Y'all might have heard about them. One of them's called capacitors and one of them called inductors. Those two devices are reactive. So their opposition varies with what? Frequency. Now one of them's called X bell, and one of them is called X of C. And we don't really need to understand it. X of C is equal to 1 over 2 pi FC. You don't need to write this down. You just need to, you'll learn it in DC. But you'll listen. I need to make sure y'all understand. So C is a unit that we use to, so capacitors and inductors are not rated in ohms like a resistor. They're rated in a value of capacitance, or they're rated in a value of inductance, and that would be L. So capacitance is given in units called farads. So you can see if the farads go up and the frequency is the same, the opposition does what? It goes down. On L, though, if the inductance of the inductor goes up, then X of L goes up. And these are in ohms, guys. So you would have 500 ohms worth of capacitance, or you might have 500 ohms worth of inductance. What you need to notice is that these formulas are reciprocal to each other, which means if I put inductors and capacitors in the same circuit at the same time, they would cancel each other out relative. Now, what do you think the F stands for? So that means X of C, as frequency goes up, opposition goes down, right? You understand? On an L, if frequency goes up, opposition goes up. If we put these guys in the same circuit, so we use these guys as filters. Filters are devices that we use to get rid of frequencies we don't want. We call them filters. You got a filter in your radio out there. So what that filter in your radio does, it allows you to tune in a station. So I can have components that are susceptible or change their value with frequency, right? And then at some frequency, if you put L and C in the circuit, they'll cancel each other out, and you have very low ohms, right? You understand? And that's what you're doing. So when you tune your radio, I don't know if you've ever looked over there, it's megahertz or kilohertz. So AM is down in the kilohertz band, and FM's up in the megahertz band, right? You understand? And you got what we call a tuner. So that's basically what you're doing, is you're setting up a circuit that allows your carrier to come through, right? That megahertz. And then you use a filter to get rid of the carrier, and now you got your audio, right? So these guys are really, really neat as far as coming in there. But what you need to understand is they're reactive, which means they vary their opposition with what? With frequency, which is pretty neat. So Ohm's law shows you the relationship between the voltage, the current, and the opposition, not R. Because the opposition could be one of your reactives, right? You understand that? Watt's law. What's Watt's law? That's the law that shows us how the power varies with voltage, current, and opposition, right? You understand that? And then we got Kirchhoff's law. What's Kirchhoff's law? There are two laws. We have voltage law. That deals with what type of circuit? Series circuit. And we got the current law that says what? That deals with what? Parallel, right? So what does it say? It says the Kirchhoff's voltage law says the sums of the voltages in the series circuit have to equal to the applied voltage, right? And then Kirchhoff's current law says the sums of the currents in each individual branch has to equal to the total current circuit. Series circuit, parallel circuits, and series parallel circuits. Everybody okay with that? And I think we talked about color code. Color codes, you're going to find these used throughout electronics. You learn the color code for resistors, but you'll run into the color code on very small capacitors. You'll run into the color code on very small inductors. We've got a diode over there. I can show you where the part number is. The part number is what color code. But it's the same color code. It's the same colors that you'll run into. We have diodes. These are electronic devices. These are diodes only allow current to flow in one direction. These are used primarily to convert AC into DC. We have bipolar transistors, which are used. These are current valves. These guys are used to control the flow of electrical current. And they give us a gain. We can get more current on the output than we do on the input. So a bipolar transistor uses a small current on the control lead called a phase to control the proportion of large current of the valve. We call the two leads the collector and the emitter. We have two types. We have a UPN and a PNP. This is going to come into play when we talk about the different DC sensors that we have. And what does the sensor do, guys? What does sensors do, guys? Sensors, you see some people call sensors transducers, which is true. So all sensors are transducers, but all transducers don't have to be sensors. Now what a sensor does is this does exactly what our sensors do. Our brain processes electrical impulses, right? So what does our senses do? Take a physical quantity and converts it over to what? Electrical quantity, so our brains can process it. So our brain cannot see. Our brain cannot hear. Our brain cannot smell. Our brain cannot feel touch. Our brain doesn't know temperature. Our brain doesn't know pressure. Our brain doesn't know equilibrium. Our brain doesn't know this stuff, right? But it knows how to process these impulses, these electrical pulses coming into the different parts of our brain, and it makes our body respond to those. So this is exactly the way our electronic sensors work. They take a physical quantity and convert it over to electrical equivalent so we can process that electrically, right? Does that make sense? We have FETs, or field effect transistors. These use so here we control the size of the current valve with a small voltage. Bipolar transistors, we control the size or the opening of the current valve with a small current. So basically, a bipolar uses a small current to control a large current, right? You understand that? And FETs use a small voltage to control a large current. And each one of them's got their characteristics that makes one better than the other. In fact, what they've done is they've combined the two. A metal oxide filament. So they combined the two features of a BJT, a bipolar junction transistor, with a insulated cage, which is what MOSFETs are, which is a type of FET, into one device. It's called a IGBJT. Because what it's doing is using the advantages of both these different types of current valves, right? You understand? One can switch faster, so the MOSFET can switch faster, but it can't control a lot of power. Bipolar transistors can switch a little slower, but they control a lot of voltage and a lot of power. So they've combined the two. Metal oxide FETs, these are guys that are predominantly used now. And then integrated circuits. Y'all heard of integrated circuits. What is integrated circuits? An entire electronic circuit on a single piece of silicon. And what they do is it means now everything starts becoming smaller, right? Especially devices that don't require a lot of power, like computers. So computers are processing ones and zeros. Ones and zeros don't require, and they represent that with voltage levels, right? Usually about 3.3 to 5 volts would be a binary 1, and a 0 volts would be a binary 0. So what's nice about the binary numbering system is it only uses 2 digits, and that's 0 and 1, which means it's very easily to represent that electrically, right? Does that make sense? So we can use voltage to represent a 1, and we can use 0 volts or common to represent a 1, 0. So you take these things that don't require a lot of power, then you can start integrating them on a single piece of silicon. So now, very small devices on a single pit. We're down in what they call the nanometer range now, where these electronic devices are extremely small. So we can get a microprocessor. We can get a microprocessor, which is an integrated circuit, which has everything that makes up a computer inside on a single piece of silicon. Well, not everything, but all the processing power of the thing, right? Billions of transistors, or billions of these transistors on a single wafer, because they don't deliver. Now they get hot. Most of your microprocessors now, they dissipate a lot of power, so they got to be heat sinking. But it's when you add all that power together, right? Does that make sense? Integrated circuits. This is what allows us to have something that we carry around in our pocket that's a lot more powerful than the first computer that was actually put out. So you got more processing power in this right here because of integrated circuits, right? Now, it still don't do away with these guys. Somewhere in my phone, these guys are in there because eventually we're going to have to hit that antenna on our phone, and we're going to have to put, a little bit of power in that, right? You understand? So we'll have, we still have these bipolar junction transistors and FET, field effect transistors. Two types of power supplies we have. We have linear power supplies. So we start off with a transformer, we go to a rectifier, then we filter that out and regulate it. These guys are, this is one of these powers, this is a linear power supply. Look at the size of this thing. The variable power supply, 0 to 15 volts, is rated at 1.5 amps. The negative is rated at 1.5 amps. And the 5 volt power supply is rated at 5 amps. So 5 amps at 5 amps at 5 amps at 5 volts, that's 25 volts, right? And then 15 volts at, instead of saying 1.5 amps, let's just say 2 amps. It is 1 amp, I'm sorry. So that would be 1 amp, that would be 12 watts, 1 amp at 12 watts, right? You understand that? So that would be 12 watts plus 12 watts, that's 50 watts plus 25 watts, right? You understand? So that would be what? Would that be 75 watts of power? So this power supply right here pulls less power than 25 watt line. This is a switch mode power supply. Its output is rated at 20 volts at 3.25 amps. That big. 3.25 amps. I'm going to put Axel's calculator to do that. That's a shame. So this guy right here is 65 watts. That thing right there is 75 watts. This is a switch mode power supply. Now, basically, the problem here is that one of the things that determines how much energy we can transfer through our transformers and stuff is the speed of the motion. Alabama Power is set at 60 cycles. And they've got all type of capacitance and all type of inductance out there in their power grid. And so they can't change that 60 cycles, right? You understand that? It is fixed. If they tried to raise the frequency, then all your X sub C's and X sub L's would give you problems, right? If they try to lower it, it would give you problems. So 60 cycles is 60 cycles. So we're stuck with 60 cycles. Well, the big advantage of DC, what's the big advantage of DC? That's what most people say, which is also true. But one of the biggest advantages is it can be electronically controlled. So I can take AC, I can convert it to DC, and then I can do what the heck I want to that. I can turn around and convert it back to AC, but I can convert it back at a lot higher frequency. If I get a lot higher frequency, then the transformers can be a lot smaller because they don't have to have as many windings, because now they can transfer the same energy with less windings. That makes sense. My filters can be a lot smaller because they don't have to filter out a low frequency signal, right? Understand? Which means the size of them can start dropping down smaller. So this is a switch mode power supply. That's what your phone charger is. It's switch mode power supply, right? Okay, now the problem with these guys is they're basically not repairable. If they break, you just can't fix them. So these guys, you have to do what? Yeah, you have to replace. That guy could fix anything inside that. So these guys, the linear power supplies, everything is still strung out, you understand, and we can fix them real easy. But the transformers have to be bigger. If I was to look at the transformer in this thing compared to the transformer in this, I can't even see it. But I'll go and get one of our power supplies that came out of our desktop computers and just look at the size of the transformers in there, little tiny things, because they're a lot more. Yeah, we got some 450 watt power supplies over there that's about this same size, 450 watts, because it's what? It's a switch mode power supply. But if those things break, we just do what? Yeah, we just don't. So this is the basic makeup of a control system, guys. What's the three things we need for a control system? For years and years, the control line was nothing but a relay. Everybody know what a relay is? Okay. What's a relay? Huh? So relay, and we'll see if we got any the internet, see if we got any. So we have a device. We know if we put a magnetic field through a conductor, it generates a. If we put current flow through a conductor, it generates a magnetic field. Everybody understand that? Now, how good we generate the magnetic field, when we start concentrating the magnetic field, we need to have what they call a coefficient of coupling. So this type of wire is called magnetic wire, which means the insulation on this is really, really thin. Basically, it's just a coating of paint. So one of the biggest problems we have with these things is something happening and these windings shorten together. If you ever opened up or looked at a transformer, it has these same type of wires in there. It's called magnetic wire. Did I show y'all the transformer? Oh, here's my transformer. This is a transformer. And when you flip it over, you can see the magnetic wire down it. And it's basically the same as this. Now this is used to concentrate the magnetic field. Now the problem we have with metals concentrate magnetic fields. But metals are good conductors, right? You understand that? So we got a varying magnetic field here, which would induce a current into this guy right here. Well, if you had a big chunk of metal in there, then your core would become a conductor. So what they do is they take it and split it into hundreds of individual little plates, which are electrically isolated from each other. So there's insulating material in between this. It's basically the same stuff that we put here. And what it does is it breaks up the core. It breaks up the core that's concentrating the magnetic field and don't allow all that current to be combined, right? You understand? They refer to it as eddy current. And that's the efficiency of the transformer. It's how we can keep those eddy currents out of this thing. So transformers do get hot, and that's because of this guy right here. That makes sense? So we call this a laminated core. And then this is the primary leads right here. And this is what we call a multi-pap transformer. This guy right here probably has a multi-cap transformer on it because we got to get these different voltages up. So this is one of the transformers out of the trainers that you use. So if you was to open that trainer up and pop that thing up, you'd find this thing. And this is a linear power supply. So what that means is it's very repairable, right? So Mr. Sanders was saying, he was saying, who do we send these trainers off to get them fixed? You know what I told him? I said, we fix them. You know, that's what we do. And in fact, that's what Cece's doing over there right now, is just getting all the trainers that we're having problems with, and what she do. Yeah, she's repairing. So here's the transformer, guys. You want to see it? Here we go. So we couple between the primary and the secondary, we couple it magnetically, which is pretty neat. Now, I got an LED. I'll go over there and hook it up on this thing, and we'll see if we can make it work. A robot over there. We got two robots that I put together, Lego robots. One of them is the one the students put together. And I'm going to have to talk to Allison about this. Yeah, I'm not going to touch it. So here's my transformer. So here's this guy right here. Here's my LED. So it's hooked up to this guy. Right? You'll see that. It's hooked up to this guy. These guys are not touching each other. And all I'm going to do is take this other coil that I got my function generator hooked up. And if I get back. So that's transformer. It's not very efficient. All I'm doing is taking this coil that's got my function generator hooked up to it, and I'm laying it on top of this other coil. Here the LED comes on, here it comes off. So what we're doing is we're transmitting energy electromagnetically. So when this guy puts AC in these coils, it's just generating a watt back and forth, back and forth. It comes over here and cuts these windings over here and does what? Is that cool? Magic. It's magic. Rich is magic. Rich is magic. Well, there it is right there. So notice there's nothing hooked up to this guy except my watt. LED, and that guy. Well, what we're going to do now is look at this guy right here. So notice this is magnetic wire. Now we need to get really good coupling. This has got a really poor coupling. Why? Because I can't get the wires really close together. And then I got regular insulation on it, right? You understand? But it's good enough to show the effect of what? Of a transformer, which is very, very inefficient. Like I said, I just want no engineering to this at all. No math involved at all. So it surprised me it worked. No math involved in this. All I got to do is I'm going to put DC on this. So the only thing that's going to limit the current in this is how the gauge of the wire, how big it is, and how many wraps I put. So you'll see a lot of wraps on these devices. What I'm going to do over here is I'm going to put DC on this. So the magnetic field never changes, right? I'm going to rip off my alligator clips off this guy. And I'm going to put it across my 5-volt supply. Now I know when I turn this power supply on, it creates a magnetic field. What I'm going to do is I'm going to take this nail and I'm going to put it up the center. And I'm going to come over and turn it on. Oh, you know, see what it does? I'm going to turn it off. Sucked it up in there, right? And I turn it off. That's the advantage of electromagnetics is not only can we control the strength of the field, but we can turn it on and we can turn it off. Well, what if I took this magnet, this metal, and I put two wires close together And when that fell down there, then it would make a circuit. So this is called a solenoid. Where do we run into these things? Anytime you need it, the only thing a solenoid does is create a linear motion, right? You understand. So here, what am I doing to make it fall out? Is I'm using the gravity, right? We could use springs, but if this tab right here fell down and touched two conductors together, then I could open and close the circuit magnetically. What's a relay? A relay is when we combine a solenoid and we let the solenoid control one or more contacts. So what we can do now is we can electrically open and close circuits, right? You understand that? That makes sense. Yes or no? Well, this is metal, so I can't do this. Well, let's say I had a wire on this side and a wire on that side. When this thing fell down, I'd touch my two wires together through another piece of metal, right? You understand? And that would do what? That would close the circuit, right? You understand that? And then I come over and put power on it. Now, up here, if I had the contact on this side, then when it pulled up, I could energize it. So we have what we call normally open and normally closed contacts. So when I energize it, so let's pause this guy. So the U.S. customary, what we run into, the symbol of a relay coil is a circle. And then we'll bring the control leads on one side. And normally, we call it energized and de-energized. Does that make sense? The symbol and then we'll give the coil a name. And usually you give it a name try to give it a name depending on what it does. Does that make sense? And then what we do is we'll come down here and we'll have these guys. This would be the symbol of a normally open contact. And then we give it the same name as the relay. So that tells us what coil controls that contact. Does that make sense? This is a symbol for normally open, and that's a symbol for normally closed. And this is a symbol. What do you think that's a symbol for? So most of the symbols are pretty straightforward. So, but yeah. But we used to do logic. So logic is when it's logic basically deals with nothing but ones and zeros. But we can do logic with this. So I can come over here and I can do this. And they're all normally open, right? And we would come up here and let's call them different. They'd all be controlled by different things. And we call this AND logic. It's supposed to be all uppercase letters, by the way, so you don't confuse it with the word AND. That means A and B and C and D would all have to be true before we can before your output becomes true. And, some of y'all had this, Brian? PLCs? Yeah, but relays, we call this OR. We got NANDs, we got NORs. But what we used to do, originally all your logic was performed by relays. Just by the way you wired the contacts. You know, you could do what we call a NOT, you could do an AND, you could do an OR, you could do a NAND, a NOR, an exclusive OR, and an exclusive NOR. You could just do that by the way you wired your contacts. So we've been doing logic long before we had computers. Long before we had computers. Well, we call it relay logic. Of course, when computers came along, we realized, and digital came along, we realized we could do logic with electronic circuits. We got integrated circuits. We got ands, we got ors, we got nors. The processor inside this computer has a main unit called an arithmetic logic unit. So basically all a computer can do is it can do math, and it can do logic, and it can move stuff around. We call it data manipulation, just moving stuff around. Just trying to get all this information up to this display screen. That's a mass move. You just wouldn't hardly believe what's going on just to get this stuff up on the screen. So just to manipulate that binary information and move it around. What's nice about these guys is these ands and these ors and these nors and these nots and these nands, all that are programmable, so we can change it from instrument to instrument with a computer, right? You understand that? So we have a programmable logic control. So originally a PLC did nothing but replace relay logic. So instead of me having to wire the relay logic, which would be decision making, right? You understand decision making. Now I could do what? I could program it into a PLC. But now your PLCs do a lot of stuff that this computer will do. They just don't do heavy graphics. They do arithmetic. They do math. They've moved data around. They can do stuff like that. So, but we still call them PLCs, which seems like all they do is what? Logic. But they do math now. So we can add, we can subtract, we can multiply, we can divide. Some of them do trig functions. Some of them do different types. It depends on which model of PLC you have. So this control section, relay logic. Do we still use relay logic? Sure, we use relay logic. Programmable logic controllers, do we run into those? More and more you do. Does it replace all relays? PLCs cannot do a lot of work. They're not designed to handle a lot of big outputs, right? You understand? But we can take that output and pull it and energize a relay, and a relay can do the work for us. So PLCs will never take the place of relays, because relays have the ability to give us a huge gain in how much power we control. So we can take a very little power to close and open, to energize and de-energize that coil, and it can control a lot of power, right? You understand that? Computers. We have computers that we can do that. We got microcontrollers. These are basically small dedicated PLCs. They're kind of PLCs, but they're a lot smaller. We have what we call Arduino. Of course, we don't have time to teach. I'll have to find that. But it's a little box. It's about maybe 3 inches long, maybe an inch and a half, maybe 2 inches wide. And it's got everything. It's got inputs. It's got outputs. Everything a PLC has, but it programs in a text-based language, and it costs like $30. So if I've got something that I don't need to reprogram a lot, and I want to replace quite a few relays and stuff with it, then you're going to see microcontrollers. PLCs are going to be a lot bigger. But eventually we're going to have to do what? So we bring in inputs, we make decisions on what we want to do with those inputs, and then eventually we're going to have to do what? Control an output with that, right? You understand? So that's like your cell phone. Your cell phone would be no good without an output on it. So what would happen what happens when your screen goes out completely? Can't do anything. What happens when of course, now we use your screen on most of your cell phones now are basic. Well, every one of them that I know of now are basically has a touch screen on it, which would be input, and then it's got the video in behind it, right? You understand? So we use it as both. It appears you're using both the input and output, but it's not. It's a membrane out there that basically acts like capacitors, guys. I'm not going to explain how that works. Everybody's interested with these, right? We have all these control devices. switches and push buttons. So we're running into a lot of these, even on our manufacturing line. Everybody okay with that? Then we have what we refer to as sensors. Now, what do the sensors do for us? Takes a physical stimulus, converts it over to an electrical signal so our computers can process it, right? Computers don't understand. It's just like our brain. Our brain does not understand sight. Our brain does not understand feel. Our brain cannot see. Our brain cannot feel. Our brain cannot, y'all understand that? Our brain cannot smell. Our brain cannot hear. What can our brain do? Process electrical information. And then electrical information makes what? Sense to our brain. So now it can say, okay, this electrical sense means I'm smelling a sweet smell, right? You understand? If I get this impulse back or this signal back from all these senses. We got, I don't know, anybody know how many actual nerve cells we have? I imagine it's way up there. So these are the these are the sensors that we're going to look at. Is this all of them? There's almost no sense that I can have that we can't electrically stimulate. Even equilibrium or balance, you know, we got what we call gyroscopes that can do what? They can sense when it gets off balance. The airplanes that I worked on had two. It had a vertical and a horizontal that did what? They could tell when the plane was doing this, when the plane was doing that. Gyroscopes. Now you can get gyroscopes, guys, that are in little old tiny things. Right? So what can we do?
It tells you when your phone is.
Yeah, we can spin it. We can play games. We can drive with our phone, right? Because it's got those small little gyroscopes in there that's working. Presence. We call it proximity. Presence is when something's at a certain spot. We can check. We can check distance. We can do position. We can do pressure, flow, light, sound, temperature, speed. And this is just some of it. That's not to say all the sensors you're going to work with. So a sensor is a transducer, but a transducer does not necessarily have to be a sensor, right? That's like I say, you know, a Ford is a car, but a car don't have to be a Ford. That makes sense? Those people that drive, like people that ride Harleys, say Harleys are motorcycles and all these other people ride something else. Luckily I had a Japanese bike too. I had a Honda Shadow. So sensors fall into two categories. We have analog and we have digital. What are digital sensors? What are they going to do? Digital sensors are going to give us two states. It's either going to say it's true or it's false. And it does that with the voltage level. Normally, it could be AC or it could be DC. The sensor can be AC or DC. I'm sorry. One sensor can't be an AC sensor and a DC sensor. It's either going to be AC sensor or it's going to be what? A DC sensor. Right? You understand? Depending on what application you want to run. All our sensors are DC sensors. Your sensors usually have a ability, a lot of your electronic sensors have the ability to run over a voltage range. Standard voltage for controls is 24 volts. So what happens is the way it's most of them are powered up, right? You understand. And then if it's true, it gives us 24 volts. If it's false, it gives us what? 0. And we can see tons of them, not tons, a lot of them on the lines. We have a limit switch. Now, a limit switch is an electromechanical device. So what a limit switch is we have a picture here of these guys. So these are basically switches that when something mechanically hits what we call an operator, right? You understand that? It's going to open contacts or close contacts. So a limit switch is what we call a contact sensor. It's got to make physical contact with a device. Now, a relay is a proximity sensor. It's going to sense when something's at a position, right? But we don't call it. It was the first guy out there, so it's got its own name. It says, I'm a limit switch. So we don't call it a proximity sensor. We call it a what? A limit switch. Then we have what we call non-contact sensors. These are sensors that don't have to make physical contact with what they're trying to measure. So digital presence, we have limit switches, we have proximity switches. So what we do when we use the term proximity switch, these are non-contact sensors. And if we say switch, what do you think that means? Analog or digital? We call that thing on the wall over there, we call that a light switch. Is it analog or is it digital? So what can I do? I can turn that light on or I can turn that light off. Is that analog or digital? It's digital. It's true or false. It's either on or it's off, right? You understand? So if I've got a light dimmer, then that would be what? That would be analog. We don't have any light dimmers in here. So we call them switches. So if we say a proximity switch, a limit switch. So normally when we use the term switch, we're talking about something digital, right? See the what? True or false, on or off. I'm surprised. I thought y'all catch on to that right off the bat. We're going to look at photoelectric. We're going to use light for a lot of things. Light's really, really neat. We call these photoelectric switches, photoelectrics. We're going to look at through the beam, optical interrupters, diffuse sensors, and retroreflective. We're going to look at inductive sensors. These work off of inductance. Capacitive sensors. We'll look at reed switches, Hall effect sensors, and ultrasonics. All of these are digital sensors that we have on manufacturing. Then we're going to have a force or pressure sensor. Flow, what's flow? Movement of a fluid. Out of a fluid. So we have flow for pneumatics. We can see how fast it's flowing. So normally what the pressure of a fluid, the pressure of a fluid system gives us how much force we can develop. The speed of the fluid gives us how fast things move, right? You understand that? So if we can control the flow, we can get the same amount of force at a slower speed. That makes sense? And y'all seen these big old earth movers and stuff where they can take those buckets and sling them around, or they can slow it way down and they can still pick up that big old rock even though they're running at the same. So they're not changing the pressure, they're changing the speed, right? You understand? So the amount of force we develop, anybody know the formula? Force is equal to the amount of pressure times the amount of area we're applying that pressure to. Very simple formula. And this is one big advantage fluids have over pneumatics. Pneumatics, we can't generate extremely high pressures because it's a gas. Hydraulics. So the planes that I worked on used 3,000 psi. So I mean, that sucker could generate 3,000 pounds of force if it was a 1-inch area piston. But you had to be real careful around 3,000 pounds of fluid. If it sprung a leak, it could come out and cut you. Yeah, it'd go right through your skin. You get that hydraulic skin into you, it could get infected really, really bad. So you had to be real careful around that. So pneumatics is a lot safer, but we can't generate as much. We can't generate that pressure, right? On the highest I've ever seen, and I didn't know it until we went up to Bridgestone, or we went to get our training for for Siemens Level 1, is they ran 600 PSI. That's the highest I've ever seen. The highest we had out at US Steel was 200 PSI. That was the highest we had. This one might can do too, but this is what we call a two-stage compressor. It might get 200 PSI. 600 PSI was a lot. They use that to form the tires, to push they call it the blanks, I think, where they push it up against the heat. Cause it to take the tread design, real high pressure. So a flow is how fast fluids are moving, not necessarily their pressure, how fast fluids are moving. Speed, we'll look at tach generators, encoders. Well, also, I don't know what's wrong. We got absolute encoders. I need to go back and look at that. Variable. I'll bring some encoders over here. It's really, really neat. Temperature, constantly measuring temperature. Temperature tells us a lot of things, right? Motors, if they get too hot, they'll burn up. Electronics get too hot, we got problems. In fact, most of your computers, especially laptops, they have a fan in there that keeps things cool. And what they can do with the temperature sensors, they can either turn it on or turn it off, but they can actually control the speed. And why do we want to do that? Of course, these guys run on batteries, right? You understand that? If it don't need to run the fan, by George, they're not going to want it. They're not going to run the fan. So we'll look at thermistors and thermocouples. We want to understand how they work. Position sensors, potentiometers, linear voltage differential transformers, and then encoders. Absolute. And yeah, this is right. This is speed. We don't use absolute encoders to get speed. We use incremental encoders to get speed. But as far as position, we use an absolute encoder or an incremental encoder. And we'll just get a basic feel of these as we move through. Yeah, and you got to understand we live in an analog world, right? You understand? Temperature. What's temperature? Is that digital or analog? Yeah, I mean. Yeah, all over the place. You know, the high today is going to be up in the 60s. The low is in the 30s. Does it go from 30 to 60 just like that? No, it varies an infinite number of degrees. If we was to go down to micro degrees, right now we'd see a change. Luckily, we don't break degrees down into micro degrees. We do degrees, right? You understand? The speed of your car, is it analog or digital? Analog. Light. Does the sun come up and then go down? It does what? We have dawn to dusk, right? And it constantly does what? Constantly varies. So light varies, temperature varies, pressure sometimes varies. You know, even the pressure in your tires. So I had to go out in my wife's van. She's got pressure sensors on there. They start flashing. Anytime it gets real cold, what do I have to do? I have to put air. I have to go back and air the tires up because cold air makes it compress or spring down. So originally, your programmable logic controllers only accepted digital information. That was it. Now most of your PLCs can accept analog information. But what it does, it runs it through what we call an analog to digital converter. What's your name? Well, if I wanted to control this, it's not this easy, guys. But one of the advantages DC motors have always had over AC motors over a time is we could precisely control them. We could control the speed from nothing all the way up to maximum speed. The main thing that sets the speed of a motor, the AC motor, is 120 times the frequency divided by the number of magnetic poles. Well, Alabama Power gives us 60 cycles. So that means pretty much, well, what we do to control the speed is we control the number of magnetic poles around things. The minimum we can have is 2. Got to have at least 2 poles in an AC motor. So that means the maximum speed a 2-pole motor would be 3,600 feet. So if you got this fan on it's got 3 speeds, it's 60 cycles, you're controlling the number of poles. So every time you pull that switch, you're switching poles in, right? Put more poles in there and the motor slows down. You know, the less poles, the motor runs up. We got 3 different positions you switch. So you just can't go in there and replace that switch. You got to replace it with that thing. It's got 1 wire coming in and 3 coming out that comes in and hooks up the different pole sets, right? So the problem we had for a long time was controlling that guy right there. So if I could control the frequency, I could control the speed of the motor, but we couldn't electronically do that and generate the power needed to run a motor. So I can control this frequency up here, but I could not run an AC motor off that thing, right? You understand? So they finally came out with these power devices, these insulated gate bipolar junction transistors, where they could control the power. So now all of a sudden we can take AC, convert it to DC, and we can output a different frequency. So now I can control the speed of an AC motor. Well, AC motors are a lot cheaper per watt, per horsepower. Well, we call them variable frequency drives, VFD, or VFDs. Well, what we're doing is most of them have this little touch panel on there that you can come up here and you can hit a button to go up and you can hit a button to go down, and you can increase the speed of the motor, you can increase it, but you have to be at the drive. I want to turn that over to a computer. Well, what we do is we input an analog signal into the VFD, and it automatically does what? Changes the frequency for it. So if I wanted to control the frequency of a variable speed drive, variable speed AC drive, I give it an analog signal to tell it what speed I want. If I wanted to control what we call proportional valves, so we have most valves that we see are either on or off. Well, some needs to control the flow rate, right? You understand? So they have what we call proportional valves, which means now we can turn them over to a computer. So in the old days, these guys would be sitting up there in these big old machines, and I'd have these big controls, and they would move them a little bit, and they'd run a certain speed, and pull it all the way back, it runs wide open. Now you get into most of them, they got these little joysticks in there, and they're controlling these big old things with a joystick. Well, what they're getting out of the joystick is they're getting an analog signal, right? And to control that proportional valve, they give the valve an analog signal, and it tells it how much to open and how much to control, so we can control the flow. Yeah, you get into these big old combines and these big old tractors now, these new ones. They're controlled by what? A little joystick, you know, because now we turn it over to a computer. So that means, and most of them will run off PLC. So that means my PLC needs to have, used to it was nothing but digital. But the more and the more we add these devices, and we're trying to control these analog devices, we can't control an analog device with a digital signal. So what we have is we have analog to digital converters. Right? And then we have digital analog converters, DACs and ADCs. So what it would do, it would give me my digital computer can output an analog signal to control the position of the valve, right? You understand, to control the speed of the variable frequency drive. But I can also use it to bring in an analog like a temperature now. So now I can bring in temperature. Instead of having an external AD converter, my PLC can do it for me. All right, you understand? So now I can bring in temperature, and then it converts it to digital, and I can say, okay, now if it gets up above this binary number represents 120 degrees. If this binary number gets up to 120 degrees, I can switch it off and on with my with my analog to digital converter. So there's a lot of needs for this. Like I said, originally when PLCs came out, they had no analog, they had no digital capabilities. Are we okay? Any questions? Yes, no. This would be a good example of this picture. So we have a very low that comes in off of the phone call. And we condition it, we got an analog output. So we have analog sensors. So we got some analog sensors on both our manufacturing lines. We'll go over and look at that. And then we have digital sensors. So this is using what we call an encoder, where it sends out a series of pulses. And the speed of the pulses would tell us how fast the pulses come, or frequency would tell us the speed, right? You understand? We have one of these on the Amatro line. We don't have any encoders on the digital line. Potentiometers, y'all study potentiometers in DC. So what is a potentiometer? What's the difference between a potentiometer and a rheostat?
Why can't you adjust the voltage?
Yeah, so that's what a pot does. A pot gives us, so a potentiometer, we call it pot for short, gives us, it's a variable voltage divider is what it is. So we come over here, and if I put 10 volts over there, and down here I set this to common, and it's a 10K pot. So if we say a 10K pot, it means if I measure between the top and the bottom, it measures 10K. But then we have what we call a wiper, that we have the ability to move across this resistor. And what we do is we can put it all the way at the top. I would get 10 volts. I put the wiper all the way at the bottom, we get 0 volts. And anywhere between, I would get somewhere between 10 and 0 volts. Yeah, we can dial it in and get it exactly what we want. Well, what if I was to come over here and move the wiper mechanically? So I put a gear out there on that pot. And when this thing's moving, I set up what we call a rack and pinion. A rack and pinion is a device that uses gears. So we have a guy like this that's got teeth in it, right? Real fast. And then we got a gear down here. And as this thing right here moves back and forth, it turns out what it's turning could be a potentiometer. Well, what would happen now, it would give me a voltage that was proportional to position. So 5 volts might mean you just move 6 inches, right? You understand? Of course, we could take that to an analog to digital converter, and I'd get a binary number that represents a position. So these are, and we can have what we call a linear pot, guys. We can have a linear potentiometer. We have 2 of them over there. We'll go over and look at them. Not right now. Hold on. So we could use this all the time. Your gas gauge on your car basically is nothing but a potential, not a pot back there. And it's got a float on it, and it moves the wiper. And if it moves the wiper, it gives you a voltage out that represents what? It represents how much gas you got in your car. You know, we can use all different types of things. So we got our cars have computers in them. You know, in the old days, we didn't have computers, but now our cars have computers in them. So there's an analog to digital converter that takes that digital information coming off your gas sensor, right? You understand, and convert it into digital, so your your body used to. It's really changed, because used to we had a engine control module, and that was it. Now we got 2 computers. We got a body control module, and then we have an engine control module. So now your lights are being controlled by, your air conditioner is being controlled by a computer. Speedometer is now, even though it still looks analog, but it's probably digital too. So this is showing us basically what's going on. This guy here is a little fast. This is an animation. It's showing us we can get a voltage, but the voltage is proportional to a position of the wiper. Are we okay? These are called encoders, guys. Optical encoders. What we do is we have a light beam, and then we have a photo detector. And we run into those all the time now. I think I was telling you I don't know if y'all been in my classes or not, but my uncle, he was always the first to get anything. And he's the first one to get the color TV in the family. He used to go over there on Sundays and watch Sunday night and watch Disney. It was color. There was only 2 shows on color: the Virginian and Disney. Came on, and everything was in black and white. So he got the first color TV, and he got the first TV that had a remote control. And it was literally a cable that plugged into the back of the TV, and he'd run the cable all the way across the floor, and they could change channels over on the screen. And then they came out with the first wireless remote, and he got that one, and it was tuning forks. And you'd press a button, and when you got too far, it would go over a plateau, and it would strike the tuning forks, and what the TV picked up was the sound of the tuning fork. And each tuning fork made it mean something. Now what we do? Well, we have infrared, right? A light source, and then we have an optical sensor up in there that senses light up in there. So, of course, you can't see it, but we can see it on this guy. So when I come up here, I'm going to try not to cover this up so I don't turn my. When I come up here, and this camera usually picks it up. Now this camera is it's a really slow speed camera. You can see it has problems picking up mine. If it was a high speed camera, you could literally see it flashing different off and on patterns, indicating which light source I was doing. You can see it flashing a little bit, can't y'all? Like this is a real slow speed camera. So what I'm doing is I'm taking this light source and I'm shooting it to an optical sensor. Well, what would happen if I was to come over here and when I covered this up with my fingers, so I came over and covered this up with my fingers, if I can get this in, and every time my finger went by, I would break the beam. Well, the faster I move it, so what I would be getting up in off of my receiver, I would be getting a series of pulses, right? You understand? But how fast I move them would be what? How fast I got the pulses. That's the way optical encoders work. So what we have is it's a unit that has a transmitter and a receiver. One of them transmits light, one of them receives light, and then how fast those pulses come back, it would indicate how fast something's moving. That makes sense. Now this is digital, because this is giving us a series of pulses. The only problem is, if I was to come up here and just put one set of bands around this would be a rotary optical encoder. Then we could tell the speed, but we couldn't tell the direction. So what they do is real neat, is they'll offset the receivers and the light transmitters. So the light transmitters would be on one side, the receivers would be on the other side, as they offset them by 45 degrees. So notice if it's moving in this direction, this guy sees the band first and it sees it second, so we get a series of pulses that look like this, and then the output would look like that. Now if we're going in this direction, this guy sees them first, right? So what we do is we see the same thing, but now they're going to shift positions. So what would happen is this one down here is going to lead, and this guy here is going to lag. So what we can do out of this is we can tell what? We can not only tell the speed, but we can also tell the direction that the unit is moving. So it all depends. These are called quadrature encoders. So quadrature is in control. So the speed of the pulses will tell you how fast something's going, right? And then, of course, which one occurs first will tell you what direction. So, then we have, now another thing that we can do with these encoders is we can tell position. So what happens if these bands are a certain space apart and they are precise, then each one of these would indicate that whatever I have it connected to has moved a certain distance, right, or a certain position. The problem is to keep up with position with this thing right here, it really don't mean anything. So when we do this with these guys, is we always have to start these at a certain spot, right? You understand? So this would be like I give you directions, and I say, go down 3 red lights and turn right, But I'm talking about from First Avenue in Birmingham, and we're sitting right here at the college, right? You understand? So anytime I give you directions, I have to give it from a reference point. Does that make sense? So if I say out this south gate right here, go down 3 streets and turn to the right, and now it means something because we do what? We give you relative position. So what we do with an incremental encoder, so this is an incremental encoder, so it gives us a series of pulses. So what we do is we have these digital counters, and then we come up and we set a position. We say, okay, so normally your inkjet printer uses incremental encoders. So what happens when you first turn it on? What do you always hear it do? What do you think it's doing? It's finding its 0 position. So it's got a sensor over here that it'll step out on purpose, and it'll come back and hit that little sensor, and now it knows where 0's at. And now it can say, okay, go out 500 steps. Well, 500 pulses, excuse me. Well, those 500 pulses is going to move it at exactly a position, right? Because these things are perfectly aligned with each other. But if I'm going to use counters to keep up with position, then I got to know the direction, because when it goes one way, we might be going up, and then when it comes back the other way, we need to do what? We need to count down. So this is where we have to use the quadrature encoder. If all I'm sensing quadrature increment encoder. If all I'm sensing is what? Speed, then just a bunch of dashes will work, right? So robots use incremental encoders. So that's the way they know. And we have what we call an origin. So you have to teach the robot where it's referenced from. So every one of them has got a set of lines. They count, they go 1, but they start from 0. What happens is the number of counts we get, we can come up here and we can take what we call, y'all know the way things work, we call them base 10. Well, the number of combinations you can get in any numbering system is you start with the base and then you raise it to the number of digits that you have. So it's actually x to the n. So just an example, since we know the base 10 numbering system, we can, with 2 digits, how many combinations can we have? Huh? 10 times 10. How many numerical combinations can we have? Now, if you have to understand, 0 is a combination. So 10 squared is 100. So if I started off counting with 2 digits, I could go from 0 all the way up to 99. And then then the only way I can keep counting is if I add another digit. Well, if I add another digit, then I get 10 to the 3rd combination, which now I can go from 0 to 999. Well, the problem we have with this is this means we have 4 bands, 1, 2, 3, 4. So this is binary, 2 bands. So that means I could only have 16 positions. That's all it can measure. After that, I'm out of whack, right? You understand? So what happens with an absolute encoder is the more positions we have, the more bands we have to have. So if I had 8 bands, that's only 256 combinations, 2 to the 8, right? You all knew that, right? If I have 10 bands, that's 1,024 combinations, right? If I had 16 bands, that's 65,536 combinations. But now we're getting to a lot of bands, right? And they're getting closer together. So absolute encoders are really good, but they're going to be limited to the number of positions they can handle, right? You understand that because of the number of bands we have. Incremental encoders don't care. You can take an incremental encoder and you can spin it, spin it, spin it. What determines how far you can go is these guys that are counting. These are electronic circuits. Dyslexic guy. The number of bands is counting, right? So your counters determines if your microprocessor's counting, good gracious, you know, you could have 64 binary bits. That's 2 to the 64th, right? With no more hardware because the processor's got that many counting capabilities. What's 2 to the 64th? I don't even know that, guy. I don't have that in the top of my head, but we can do it real fast. I'll bring up my calculator right here. And I can say 2 raised to the, where's my y to the x? So that's the processors that we're dealing with right here. 2 raised to the 64th power. That would even be past our, I think they're saying we're approaching, what, $746 billion of debt now. That's not, this guy would be saying, a small change, right? So 64 bits, good gracious, these processors, and this would be incremental encoders, because the incremental encoders don't care how many times it spins around. All we got to do is start it from an origin, right? You understand? And then, you know, I could have 200 pulses per revolution, but that's 200 pulses per revolution. How many revolutions can I make? How many I want, yeah. And we just keep counting. So this is one of the biggest advantages of an incremental encoder is that, good gracious, you know, like I said, 64-bit processors, if you just use a single, we call it a quad word. We just use a quad word, that's this number right here. Gosh, I can't even say that. Can y'all say that? That's a big number, right? Robots have no problem with that. So now I can use incremental encoders and put like 1,024 pulses and then gear it so it looks like I'm getting twice that many, right? And now I'm down to nanometers instead of millimeters, and we can put these robots on just about anything we want to. We just can't comprehend how accurate these suckers are. We just cannot comprehend. We just don't understand. As long as you maintain that end of arm tool, as long as you keep it within specs, right? So how often do they change the tips on those?
Robot? Every day?
Every day. You know, some place like,
Like 4 or 5 days.
Because they're trying to keep it so accurate. Because if you're positioning down really, if you're really, really close on your specs, if the tip starts wearing out, then your specs is going to be whatever your tip's at. My little welder at home, I burn them up, and because it's depending on me, it's not depending on a certain position. And these guys work off. So here's the incremental. So this is the quadrature right here. If you change the position, these would count pulses right on these and that. So it's actually giving us a number depending on these. These are rotary. They can also be linear. Y'all know what linear means? What does linear mean? Well, linear, straight line, yeah. Rotary means this thing. Are we okay? So, did I exit that? No, I didn't. So what we're going to do next class, if everybody shows up, we'll do a lab. And I don't know about Anthony. We might have to do something about him. He's training for a new job.
Is that for safe?
I don't know where he works at.